Okay, then we continue the lesson for the combinatorics. This is just the permutation again, but if you remember, let me just recap a little bit. So if I give you three distinct objects, for example, some number of distinct objects, let us say A, B, C, and D. Assume that these are distinct, of course they are distinct, but then you want to arrange them in a row or whatever, but somehow, for some reason, the order matters for you. It is important for you to keep the track of order. Then that is called, so if I write that is any item that includes all of them in one particular order, for example A, B, C, D, is a permutation, is a permutation of these objects. For example, A, B, D, C should be considered a new item, yes? Because the order in A, B, D, C is different from the order in A, B, C, D. They are actually recognizable that they are different. So this is one permutation, this is another permutation, yes? And if you want to count the number of permutations, all the permutations here, we learned that if I have n distinct objects, yes, so that is important, the objects are distinct, and if you want to arrange them in a row, or so that the order matters for you, we learned that how many items will be there. We learned that the number of items is n factorial. Yes? So this we learned. For example, in this case, if I ask you how many permutations of these four letters you have, the answer is 4 factorial, and if you calculate 4 factorial by 1, 2 times 3 times 4, it becomes 24. So there will be 24 of them. But now let us assume that some of them are repeated. Yes? So let us see in that case what will happen. For example, let me give you a very simple example. If I have just A and B, if I ask you how many permutations you will have of these three objects, the answer definitely is not 3 factorial. Yes, it is less. Because interchanging these two A's will not change the item at all, so I cannot count it 2 times. So if I ask you how many permutations you see here, what you can do is this. You can say that, okay, let me write, this is very simple. I start with A, B. One other possibility is to write A. Let me write it in this way. A, B, and A. Yes? Is there any other possibility? I can have B, A, and A. Yes? So these are the only options, yes? Agree with me? Because either B should be in the third location, or in the second location, or in the first location. There is no other choices. Yes, so it is, there are 3. And then you see that this is not 3 factorial, because 3 factorial is 6, but you see that you have only 3 of them. Okay, but we want to find a formula for this. Okay, sometimes we do not have a very straight formula for that. We have to count different items, different categories of items, and add them up. But sometimes we can write a formula for the whole idea. So, for example, let us try to find a method that we can somehow extend it if I have more objects and more diversity of repetitions. Yes, let us see. Let us try to understand this a little bit better. One strategy is to momentarily assume that these letters are different, even though they are not. So by labeling them A1, A2, and B. Yes? So if now A1, A2, and B are 3 distinct objects, well, we know what is the number of permutation of these 3 objects. But let us look in this way. The idea is this. I write A1, A2, and B. The point is that I do not want to touch B. I will keep the location, the position for B as it is, but I interchange these 2. Okay, so it becomes A2, A1. This is recognizable. This is different from that. But if I go back and erase these indices, they are exactly the same. So here, if they are different, I have to count them 2 times. But if I remove the indices, this is just 1 time, 1 item. Is that understandable? Okay, let us go to another scenario. I would write A1 here, B here, and A2 here. Okay? And then I keep the position of B as it is. I interchange these two. It becomes A2, A1. In this form, this and this should be counted 2 times. But if I remove indices, this item is exactly the same as that item. And let us just be patient, do it once more for this case. Yes? Is that understandable? Okay. Now, what is the height? So you can see that that is a rectangular array of items. How many columns you see? I see 3 columns. How many rows I see? I see 2 rows. Okay. So this is 2 rows. And then how many items are here? There are 3 columns. So in total, if you want to find the number of items within this rectangular array, it is very simple. What do? You just multiply 2 by 3 and you get 6. Okay, but in this scenario, if I remove them, so if I remove these indices now, yes, there is no difference between this one and that one. But even if I remove the indices, this one is still different from that one. Yes? And this one is still different from that one. So it means that then the number that I am looking for, x, which is the number of permutations of these 3 objects, is actually this width. Yeah? So let me write it in this way. So this is the number that I don't know, and I want to calculate that. 1 from this column, 1 from this column, and 1 from this column, yes? Of course, I know that this is 3, this is in front of me, but in principle, this is exactly what I want to count. Assume that you don't know that. But you know something. You know that when I multiply x by 2, it becomes the total number of permutation of these objects. Yes? So it means that it becomes 3 factorial. Is that understandable? So let me repeat it again. So before erasing these indices, what you see in this table, you will see all possible permutations of these 3 objects, which you already know is 3 factorial. Yes? So you know the total number of items in this rectangle on the one hand is 3 factorial. On the other hand, it is equal to the number of columns that I pretend don't know yet, multiplied by the height that I will tell you why I know 2. Then I am looking for x, so x becomes 3 factorial over 2. Yes, and that is the reason this 2 is coming. Okay, might be it is not very clear. Let me give you another example. Okay, so let me give you 3 A's and 2 B's, and I ask you the same question. How many permutations of these objects are there? I have 5 items. 3 of them are exactly of the same type, and 2 of them are a different type. And I want to see if I arrange them, how many ways I can arrange them. Yes, do you want to say something?
10?
No.
No, 2.
I don't know the answer. 10, yes, 10. 10, yes, that's correct. Yes. But the strategy is important, the strategy of counting, yes?
I thought
Yes,
yes.
but-
No.
So the strategy is important because if I give you this problem, I don't know, can you just immediately understand what to do? For example, the number of permutations of these objects. 3 A's, 3 B's, but 4 C's, for example. We want to find a recipe to be able to answer all these questions very easily. Okay? I want you to learn the strategy. The strategy is exactly these indices. Okay, so what I do, I momentarily think that these are different objects. Okay, but I want you to understand my strategy. Let me write it a little bit nicer so that we can have enough space. So I would consider that I have A1, A2, and A3, and I will have B1, B2. Okay, let me ask you one question. If I remove all these indices, this is an, do you agree that this is a desired item, yes? If I remove all these indices, that becomes one permutation of these objects. Is that right?
Yeah.
Okay. Now, what I do, I want you to do this. For example, I would write A1, for example, and then I would write B1, I write A3, A2, and B2. Yes? Okay, let me ask you one thing. If I remove the indices here, do you still agree that this is also a permutation of these objects? Yes? But now look, if I remove the indices here, and if I remove the indices here, should I count them 2 times or 1 time? 1 time. So if I remove the indices here, it becomes A, B, B. If I remove the indices here, it becomes A, B, B. Are they different or the same? Different, yes? So it means that what you see here, even after removing the indices, will be different if I remove the indices. So this is one of the items that I am interested in as a permutation of these objects. This is another one. But now look, what I tell you, try to consider all possible scenarios that you interchange A's within themselves and B's within themselves. Okay? So it means that, for example, one scenario is to write A1 here, A2, A3 here, A2 here, B1 here, B2 here. For example. Yes? But be careful. If I remove these indices and these indices, are they different or the same?
Same.
They are the same. But right now they are different. Okay? So be careful about it. Let me just do another thing. So I, for example, write A3, I would write A2, A1, I write B2, B1. Yes, this item right now is different from this item. We can recognize that. But if I remove the indices and this one, all 3 items collapse into one new item. Yes, that's just one item in this scenario. Yes, in this scenario, 1, 2, 3, 4 up to here. But in this scenario that there are no indices, all of them should be considered once, and this is another one. So far on the board, I have only 2 items. Is that right? Okay, now I will do the same thing. Here, the strategy is if you want to interchange A's in the same locations as A's and change B's in the same locations, but keep them in the same locations as B are. For example, instead of A1, I can write A3. In this one, I can write A2, A1. Here, I can write B2, B1. Yes? So this, I want you to understand the strategy. Whenever you write an item, in that column corresponding to that item, you are only allowed to interchange A's within themselves and B's within themselves. And you produce some items here. Yes? Do the same thing for the second column. And then continue this until the very last column. I don't know whatever it is. But I want you a little bit of your imagination here. If I am patient enough and complete this table, first of all, I want to ask you how many items will be in this table? 1, 2, 3, everything if I count. How many items will be at the end in this rectangle? Yes? 5 factorial, isn't it easy? Because what you are doing, you are interchanging everything with this. So if you consider all possible scenarios, it means that you are considering all permutations of 5 distinct objects. Yes? So in total, the total number of items is 5 factorial from our previous studies. But what are the ones that I want to count? Do I want to count all of them?
No.
How many of them should be counted for each column? Yes? Only one. For example, the first one. Because if I remove the indices, all these items become exactly one item. So what is important for me? But if I remove the indices, this one is different from this one, yes? So this length, I still don't know. Yes? I don't know how many columns are there. Yes? That's exactly what I want to answer. But I think you can tell me what is the depth of this column. All these columns have the same depth, and what that is. So I haven't written down. For example, I can continue. What I'm supposed to do. I can start changing A's among themselves, changing B's among themselves. For example, I can start with A2. And then I write A1, A3. Then I can write B2, B1. Should I stop? No, I can even continue. I can write A2. I can write A3, A1. I can write B2, B1. Yes? So I don't want to write all of them. It's not hard, by the way, to write all of them in this case. But before doing that, what is your prediction? This is something you can use a combinatorics again to count the depth, to know the depth of each column. Anyone else? So what I told you, learn this strategy. What I am doing, I am interchanging A's among themselves and interchanging B's among themselves. So how many ways I can arrange A's and B's in this particular way? 3 factorial? That's not enough. 3 factorial only takes care about A's.
4. Oh, I thought you were...
Yes, Dima? Times 2 factorial. Yes? So you see, 3 factorials is the number of ways that I can interchange A's among themselves. Is that right or not? I have 3 objects. I have 3 distinct positions. I want to replace A's among themselves. So why do you even look at B's? I want to interchange A's. Yes? In how many ways I can do that? 3 factorial. But now in how many ways I can interchange B's? It is clear 2 times, but of course 2 factorial is also the same number. But I multiply them because I want to arrange A's and B's, one after the other. So this is the total number of ways that I can do this arrangement, which if you calculate 6 times 2 is 12. So if you really take care of all of them, it becomes 12 items. But if you remove the indices, all these 12 items are exactly one item. And that item is A, B, B. Yes? But when I go to the next one, I want to make sure that you understand that the depth is still the same. Because here, A's are in first, second, and the third positions. B's are in the fourth and fifth position. Here, I have to decide to put A in the first, third, and fourth position, and then here at 2 and 5. So here, I am not allowed to move A to the second position. I have to keep A's in the first, third, and fourth column. But it doesn't matter. Number 1, number 4, number 3, and number 4. They are distinct positions. I have distinct objects. I want to arrange these distinct objects in distinct positions. How many ways I can do? Again, 3 factorial. Even though the positions are different. And for the same reason, that would be 2 factorial. Is that understandable?
Yes.
So what happens is that, if I ask you to count the number of items in each column, with this strategy that I mentioned, I hope that you agree with me that the depth of all these columns are the same, and it is 3 factorial times 2 factorial. Yes? But now, if I ask you how many items are in this rectangle, you can do it in a different way. You can say that I have X columns, which I don't know, multiplied by the depth. But I know the answer should be 5 factorial. Yes or no?
Yes.
And then I am looking for this X. So X is how much? And if you calculate this, really it becomes 10. Yes? But I think in this way, now you have a very nice idea how to do it. So this 5, what is 5? 5 is the total number of items appear. Yes? But you cannot write 5 factorial because this is only for the case that all the objects are distinct. But now 3 of them are of this type, so you get the 3 factorial down in the denominator. And then 2 of them are in that way, so you divide it. So it is a very simple formula that you can use even if you have repetition in your items. Is that clear? Yes or no? So can you now answer this question? So let me add one E at the end. Let me add one E at the end, yes. So what's the answer to this? 3 A's, 3 B's, 4 C's, 1 E. I want to find all possible permutations. How many of them are there? Yes? What? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Yes, you are right. 11 factorial.
Divided by 3 factorial times 3 factorial times 4 factorial times 1 factorial.
Times 1 factorial, which we don't usually write.
Yeah.
So that's the exact answer to that. It's very, very simple. So if you have repetition, but be careful. I am using all of them. If I say that, okay, how many ways I can choose 3 of them and arrange them, that would be a horrible problem. So it would be hard. Yes, because there are many kind of combinations we have to use. Be careful. I am using all of them. Yes or no? So is that clear? So for example, I can write this example for you. So how many words one can make, how many 11 letter words, 11 letter words, one can make with the letters in the word Mississippi? This is a very, yes, I think this spelling is correct. Yes. So, this is a very favorite word in combinatorics because, so this is the Mississippi River, yes? And then you want to actually see how many 11 letter words you can make up with the letters in. This is, I told you, it's a convention. So it means that you have to use, so first of all, 11 letters. Let me see that. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Yes, that's correct. So then they will ask you, for example, to write this. It means that you have to use I exactly 3 times. Because it has been, 4 times. It has been repeated 4 times. Okay, how many ways I can, how many words, meaningless or meaningful, we don't care. Pronounceable or non-pronounceable, we don't care. So, what is the number? Yes?
11 factorial divided by 4 factorial times 4 factorial times 2 factorial times 1 factorial.
Yes, exactly. So what I do, I write Mississippi like this, M-I, and then I have S-S-I, again S-S-I, and then I have P-P, and then I have I. Yes? So I have 1, 2, 3, 4, 5, 11, yes? But then you see 1 is repeated 1 time, so you can write 1 factorial, you just totally ignore that, but I have 4 repetitions here, I have 4 repetitions here, and I have 2 repetitions here. That's the answer. Yes? Okay, let me make it a little bit more tricky. This is not easy to answer usually, but for this case, I ask you how many 10 letter, intentionally I made it 10. If I ask you 9, then it is hard to answer. But how many 10 letter words you can make up with the letters of the same word? It means that you need to choose to throw away one of the letters, yes?
Yes.
So, 11 letters, we answered. How many 10 letter words? I want to pause recording the video so the people at home, it is clear, the same word, instead of making an 11 letter word, I want to make a 10 letter word. How many 10 letter words are there? So I will pause recording to let you think about it. No, don't use the calculator because if you read the answer, I will not recognize that.
So,
but if you just give me the answer in the form of factorial,
Okay.
might be I will be able to understand what's going on.
Okay.
Okay, any ideas how to proceed? Yes, Kevin?
I make a 4-stage task out of it.
Okay, I'm hearing you because you might have a different idea, yes.
So I take into account 4 scenarios.
Okay, that's good now, because when you said 4 stage, I was a little worried. Okay, now it's correct. 4 scenarios.
4 scenarios.
Yes.
One for each letter that you
Exactly.
remove.
It's very, very natural, yes? Okay, but let me just do what you said. So, you say that, okay, I want to have 10-letter word. A 10-letter word means that I need to get rid of one of these letters. Okay? In one way is to get rid of M. So forget about M. S, okay? And then what is left for me? So I do not have any M's, so it means that I need to calculate this. So how many letters are there now? 10 of them. But 4 of them is repeated. 4 of them also repeated. And this is 2 factorial. If someone asks you write a sentence for it, I would say that this is all possible 10-letter words not containing M. Yes? Is that clear? But this is not the only scenario. It might contain M, but does not contain one of these I's. So, and they don't overlap. This is important. Because every item here does not have M, but in the next category, I want to get rid of one I, but I want to bring in M. So the words that I write here are completely different from the words that there is no overlap. If there is an overlap, I will not be able to use the sum rule. Yes? Okay. So then, I hope that you agree with me, it becomes 10 factorial. Then I is gone. So this is 1 factorial, so forget about it. 3 factorials are here. And then 4 factorial and 2 factorial. Yes? I need to add them. The other scenario is very similar, and I think you agree with me, the number is exactly the same, even though I want to get rid of one S. But that would be exactly the same thing. 4 factorial, 3 factorial, and 2 factorial. And finally, I get rid of one of these p's, and then what happens? It becomes 10 factorial. 1 p is gone. I have 1 p here, 1 m here. I don't need to write 1 factorial, 1 factorial, but I need 4 factorial, 4 factorial. Okay, what I want you to do, really I want you to explore this. I want to take your calculator and calculate now the final number for this. There is a reason that I'm telling you this. So I want you to calculate this. In any way, I want the final number. If you want, you can do it in your head by calculation, or you want to do it with algebra, or I want you to calculate that. I want to wait just 1 minute. Yeah, you can use your calculator.
Jag har sett det, men jag vet inte vad jag ska...
Okay, let me myself do it. Without calculator is also possible, at least to some point. For example, between these two, if I add these two and take away these 2 factorial, do you agree with me? I add these two, but the effect is just removing 2 factorial. Do you agree that?
Wait.
I add this one, the answer to this part is this. Do you agree with me or not? Yes? Because this one is exactly the same number. If I add it to itself, it becomes 2 times larger.
Yes.
And if I multiply 2 and 2 factorial, the same, so they are gone. So the answer to the middle one is that. But then, what happens here, I have 10 factorial here, and then I have, let us look at the denominators. I want to make a common denominator. Okay, so can you tell me, instead of these two, I write that, and between this fraction, and that fraction, can you tell me what should I write as the common denominator? So you see, I put a 4 factorial, taking care of this, taking care of this, taking care of that. Yes? I need another 4 factorial. This 4 factorial that I am adding will also take care of this one. Also take care of 3 factorial. Because 4 factorial is 4 times 3 factorial. So I don't need to be worried about that. Also takes care of about that factorial. Yes? Okay. And do I need something more? I have another extra 2 factorial here. So I want you to understand how to manipulate these factorial symbols. So do you agree that this is a good common denominator? Probably the optimal one. Yes? Okay, now if I divide this by that one, it becomes 1 times. And I multiply this here, it becomes 10 factorial. Yes? And then I go here. If I divide this in your head to this one, what is your answer? Can you tell me? Divide that by this in your head. The denominator by the denominator. What's the answer? Yes? No? Yeah, it is. Yes, you're right. Yes, you said 8. Yes, yeah, I was thinking, okay. So 4 factorial and 4 factorial are gone in your head. 4 factorial divided by 3 factorial is 4, but there's an extra 2 there, so it becomes 8. And I have to multiply 8 here. So it becomes plus 8 of that. Yes or no? And then, what happens here? Only 2 factorial left. But 2 factorial is 2. Multiplied here. But then what happens? In the numerator, I can write it simpler. What is that? I have 1 10 factorial here. 8 more. 9 times 10 factorial so far. 2 more. How many of them are there? 11 times 10 factorial. Divided by 4 factorial, 4 factorial, 2 factorials. But 11 times 10 factorial has a better name. What is that? So it is 11 factorial. Okay, so I mean that I want you to learn these things. So we were able to combine all this into one. Okay, and then there is a surprise for you there, isn't it? That's the same number. Yes? But I could predict that. That's why I asked you to do this. How could I predict that this is going to happen? So you see, this number that I get at the end is exactly this number that you have here for 11 letter words. Of course, 1 factorial doesn't make any difference. So, the number of permutation of 10, this is something that I could see and ask you to do this. How could I see this? I didn't do the calculations, by the way, so quickly in my head. I did it a different way. And I was hopefully that this will work. This is why I didn't want to do it before I might do the calculation. But why do you think I could predict that they have to be exactly the same number, even though I am counting different things? I am counting 11 letter words here. I am counting 10 letter words here. But it turns out to be exactly the same number. Why is that? Could you see easily that this is going to happen? Now that I have drawn your attention to it, you need to find a reason behind that. The reason that I want you to think a little bit, this is a very deep concept in combinatorics, and that is called one-to-one correspondence. Yes. So the notion of one-to-one correspondence is very, very important concept, And that is the reason actually behind the counting. We have already talked about this. For example, if I have a set of collections here, and I have a set of collections here, if I can establish a one-to-one correspondence between the items in one bag with the items in the other bag, then even though I don't know how many of them are there, I know that the numbers are the same. Yes, that's the idea. So for example, one-to-one correspondence means, for example, I connect one of these to one and only one of these. I connect one of these to one and only one of these. I don't know if I connect this one to that one and this one to this one. You see, this is a one-to-one correspondence now. If you have this, so you see, if this is the real, oh, it's not done, okay. So here, what you see is that the number of items in the left bag is definitely equal to the number of items in the right bag, even if I don't count them. This means that I have established a one-to-one correspondence between these items and those items, yes? If I have something extra here, then it is not possible to have a one-to-one correspondence because there is something left without being any arrow attached to it. If I want to attach another arrow from here to there, this is no longer one-to-one. This is two-to. This is one-to-two. Yes? I want to keep it one-to-one, and I want to finish it. I hope that you agree with me that if you can establish a one-to-one correspondence between the elements of two sets, they have to be considered to be the same. But now let me ask you this question. Before going to this, a little bit tricky, but let me ask you, see, I give you 4 items. By the way, this is not very strange. If I ask you, let me see. Okay, but you can ask. If I ask you how many, this is a very simple setup. Let me make it even simpler. If I ask you how many 3-letter words I can make with ABC, let us not confuse you with repetitions and things like that. I have 3 distinct objects, and I ask you, how many 3-letter words I can make from this? 3 factorial. Now I immediately ask you, how many 2-letter words I can make this? Yes?
3 factorial.
It's again 3 factorial. You don't believe that you can do that. What I do, I would write ABC, and then I would write what? ACB, and then I write BCA. Let me keep the order. BAC, BCA, and CAB, CB. Agree? These are the all 3-letter permutations, 3-item permutations. But now, what I do, I tell you, drop the last letter from each one of them. What do you get? You get AB, you get AC, you get BA, you get BC, you get CA, you get CB. Now, can you imagine another 2-letter word from this which is not written here? So it is a one-to-one correspondence. You see, I am telling you, give me an item with 3 elements. I take the last one away. I will get an element with 2 elements. It is in this bag. And but you need to be careful. In order to establish a one-to-one correspondence, you should go back and forth. If you give me a 3-element item, I drop the last one. I reach to this one. But if you give me this, how should I go back? I see which letter is missing, C, I put it at the end, and I will get this one. For example, so which one is connected to this? A is missing, put A at the end, it becomes BCA, and BCA is here. So you can go back and forth, and then for each item here, you have one item there connected to it. So it means that the total number of items here and the total number of items are the same, even though they are different things. Yes? And that's exactly the same thing. And I hope that you agree with me, repetition doesn't matter at all. You can just go at the end and drop the final letter. You get a 10-letter word. Or you go to the 10-letter word, 1 letter is missing, put it at the end, you get an 11-letter word. and you can continue it. So without counting this, you should be able to see that they are the same. And I hope that you agree with me that this analogy cannot be pushed so far. I cannot say what is the relation between 11 letter words and 9 letter words. This is not working like that. You should be able to convince yourself about it. So, okay, is that understandable? Okay, now let us try to solve a little bit more interesting problems, okay? So I give you this. Okay, so, but at least it means that your understanding is quite good because you were able to write this yourself. And by the way, it is not trivial. I don't know, did you calculate this number using your calculator? So let us calculate this one. This is 11. I don't know if you can calculate it. 10 and 9, 8, 7. Oh, it's big. Yes. 7, 6, 5, and 4 factorial, which is gone here. 1 factorial, I don't need it. This is 24 times 2. Yes. So this one and that one 3 times. This is 6. This is gone. Yes. And then what happens? This is, I don't know, 90 times 11. This one, I consider that one multiplied by 35. So that is the number. Yes? But you see that you were able to, I don't know, this is a little bit, so it is around 30,000 items. So you should be able to, so you see that you actually did very good job. You were able to calculate nearly 30,000 items in a limited amount of time. Yes? And if you don't believe in that, I really recommend you to write a code. If you want to actually improve your programming skills, actually it's a very good place to do that. Write a program. It's a very simple. Probably you have internal functions, like depending which language you're using. Probably you can immediately write the permutations and things like that and see what happens. Okay, now let me ask you one question. In how many words, let us concentrate on 11 letter words. Okay? In how many of them letters of the same kind are adjacent? Okay? In how many of them? So I mean all I's are next in a block, all S's are next to each other, and all P's are next to each other. Of course, M is single. In how many of them this is happening? Is the question clear? So for example, is this word an acceptable one in this case? No. Because I have 2 S's next to each other, but there is a gap between these 2 S's and those 2 S's. I want to have S's next to each other, I's next to each other, P's next to each other, and of course F. In how many ways I can do that? I want to hear your strategy. The number is not that important. Yes, Dima?
I mean, I think the strategy is that there is 4 different kinds of letters.
Kinds, yes. Exactly, like the one that we did for math books and physics books. Do you remember? We put these things in my head in a box. Yes? I don't know, I can put it in a little bit different box so that I can differentiate this. This is another box. If you do not look inside, you have some objects. One of them is a letter. The other ones is something very strange, but these are objects. Yes? And how many ways I can arrange them? All of them are distinct now. Yes? So how many ways I can arrange these objects? 4 factorial. Okay. Okay, and then what? And then what? And then nothing. Yes? That's the answer. Yes or no? Because in the case for books, after arranging them in the box, then I actually go into the box and arrange them within themselves. But there is only one way to, of course I do that, but it doesn't matter if I interchange the i's. So if you want to, you multiply by 1 factorial, this factor, 1, 1, 1. So that is the answer, if I want to keep all of them. Yes or no? Now let us solve this one. Only keep S's, all S's next to each other. That is only constraint that you have. I want to keep all S's next to each other. I do not have any constraints regarding the others. They might be next to each other or not. All S's, let me clean this. This is now the new situation. All S's are combined, but then what? How should I write the number of items? Anyone else? Yes? So I don't know, let me see. 1, 2, 3, 4, 5, 6, 7. So you said 8 factorial. Yes? Yeah. 50% correct, 50% wrong. Pardon?
7 letters and 1 box.
Yes, that is 8 objects. But if you write 8 factorial, it means that you are considering all objects are different. But how many different objects you have? This curly shaped object is distinct, but not all eyes are distinct now. So you see how you have 8 objects, but 4 of them are repeated, 2 of them are also repeated. So you have to divide by 4 factorial, 2 factorial. And then you don't need to be worried about arranging these things within themselves because that will give you only one possibility. Is that understandable? Everyone understands what's going on? So if we have this in one box, then this would be the answer. Yes or no? Okay. Let me ask you one question big for you. Okay. Consider the word constitutional. This is a good question, by the way. So, consider the word constitutional. Yes? If I ask you how many words, this is simple. If I ask you how many words, how many 14 letters, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, yeah, that's correct. So how many 14 letters I can make with this word? This is a very standard question. It's very standard, yes? So I recommend you to write it like this. Constitutional, yes. Yeah, that's easier for me. I don't know. That is the way that I have invented for myself. Okay, but this is constitutional. If I ask you without any constraints, how many 14-letter words I can make up with the letters in this word? What's the answer? No, we don't need to wait. This is standard. I don't want you to give me the answer just in factorial form. So I know that I have to have a fraction. So 14 factorial in the numerator. Let us keep the order. This I don't need to bother. That's 1 factorial. But this is 2 factorials. 2 factorial. I don't need to worry about S. 3 factorial and 2 factorial. Yes? So this is the total number of 14-letter words that I can make up. Let me ask you one question to see if you remember. How many 13-word letter I can make up?
You just changed the
No? Yes? The same number. Yes? You remember I told you. There is no difference between the total number. Okay. But now my question is that how many of them start with a vowel? I want you to think about it. How many of these words, how many 14-letter words, 14-letter words starts How many start with a vowel? I want to wait for you because that is the nature of this kind of mathematics. The questions are easy, but answering them might be really hard. So the people at home, you know the problem. So we have the word constitutional. I am interested in 14-letter words made up from these letters, but I want one constraint. The word should start with a vowel. I pause the video. Yes, and you just need to tell me your strategy. You don't need to be very detailed.
So I thought like, how many vowels do you have? You have 4.
So yes?
Yeah, and then 5 consonants. So I took each vowel will have 5 different ways of writing the consonant. So it's 4 times 5 factorial.
Are you sure that you are not ignoring some cases?
Probably.
Yes. Oh, because that's important to understand. That is the whole point. So what you are saying, you can repeat if I can detect your, because the answer might not be that simple. So what's your answer?
I have a different strategy.
No, let me ask here from Amanda. What do you have the final answer or not?
Yeah, 4 times 5 factorial.
Okay. It doesn't seem reasonable. Yes? 5 factorial is just 120. It's 480, you mean? Yes? But 8 factorial is already 40,000 or something.
Yeah.
Yes? So what about 14 factorial, even if you are dividing by some numbers? The numbers we are dividing are not big. Yes? That is 2, 2, 2, and 6. Yes? Even if I just divide that 8 factorial by 6, I will not get to that number. Yes, probably. Yeah. Now I want to hear from you. Yes.
So instead of creating a 14-letter word, I create a 13-letter words starting with each vowel.
Yes.
So first I choose O, and then I do 13 factorial divided by all of that.
Yes.
And then I start with I, and I do the same, and then I add them.
That's correct. I think that's a very reasonable strategy. Yes. Let me just do that. I will come back to you if that's different from this. So what you say is completely right because you say that I want to start with the vowel. So the vowels are O, I, U, and A. Yes. We want to start with the vowel. You say that okay. Let me start with a simple case. Let us start with A first. Yes. So I put A in the first position. And I can ignore A for the rest of the calculation. I put A there, and then I will start arranging them. And I'm not worried about taking care of starting with the vowel because I have already started with the vowel. Yes? So how many ways I can do that? It becomes how many letters are left? 13 factorial in the numerator. A is gone, remember. A is not there. And then what happens? I have 2 O's, and then I have 2 N's. Then I have 3 T's, and then I have 2 I's. Yes? Agree or not?
Yeah.
This is the number of items if I start with A. Immediately, I hope that you agree with me, there is no difference in number if I start with a U. So even if I start with a U, I will get this one. Instead of adding this with itself, I just multiply it by 2. Understandable or not? If you don't like it, you can write it once more and add it. That would be the same thing. Okay. Now I considered the case of A, the case of U, but the case of I have to choose one of them. So one of them is now gone. So this means that I start with the I. So this is start with an I. So how should I count this? How many are there left? 13. Yes? 13 of them are left. And then what do? You have 2 factorials here. 2 factorials here, and then 3 factorials here.
Wait, vilken bokstav är det?
Yes?
I.
I'm starting, this is A,
And U.
another U,
Okay.
now this is I. I is gone, but one I is left, so it should be counted here. Yes? One I use, another I is left for me. So this is why I wrote it like that.
Times this also.
Are you doubting, Dila?
Should it be 2 times this?
No, yes, it becomes 2 times this because the situation that's not because of the I, because of O.
Oh, yeah.
Yes, it doesn't matter because when I start with I, you cannot recognize which I have put first.
Yeah.
But the problem is symmetric with respect to O and I. So it doesn't matter. If you want now, I can start with an O. I hope that you agree with me. This 2 factorial before was for O. Now this 2 factorial is for 2 I's left. But the answer is the same. Do you agree with me? So it means that I have to multiply this by an extra 2.
Yes, but then
Yes? And then what do? I add them. Is there any other scenario that I have left? No.
no.
I have considered all of them. So that's the number. And that's good. If you can write this, it means that you have done actually a tremendous job.
Fick samma.
But let us simplify this again, if I can do that. So these 2 and that 2 are gone. Yes, so let me, this 2 factorial and 2 are the same actually. This 2 factorial and that is gone. This is not needed in the exam, but I want you to improve your skills here as well. So what do I have? I have 2 factorial, 2 factorial, 3 factorial, and then I have another 13 factorial divided by 2 factorial, 3 factorial. If I take the common denominator, I hope that you agree this will play the role of the common denominator. So this becomes that. And then this is 1 times. And this is how many times? 2 times. Yes? And then if I add them, it becomes how much?
3.
3 13 factorial divided by 2 factorial, 2 factorial, 3 factorial. But let us simplify as much as I can. So the numerator becomes 13 factorial. But this is 6 factorial, so it becomes 8. So now your answer seems not right, yes? This is the correct answer. Am I right or not? Yes? Because this is 6. 3, 6 is 2. 2 times 2 times 2 is 8. Yes? Is that understandable? But I want to tell you another strategy, which is also nice. Okay? But it is harder to understand. But if I want you to understand, okay? It's not. It's a little bit out of reach. You need to be experienced. Instead of counting this problem, I change the scenario. Okay? I will bring in 6 letters of X. Yes? How many vowels are there? 1, 2, 3, 4, 5, 6. Instead of all the vowels, I put X. Yes? So I put X. So I write it like this. X, 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 and X. 1, 2, 3, 4, 5, and 1 more. Yes? And then I will keep O. No, not O is gone. Vowels I don't consider. C. I have N, N. I have T, T, T. And though I do not have these vowels, I have L. Instead of solving that problem, I consider this problem. Yes?
You forgot S.
Pardon?
You forgot S.
I forgot this. Thank you. Thank you very much. Thank you. I forgot this. Thank you. That's this. So you see, of course, the vowels, I want to look them in the same way. I replace all of the vowels with X's. Okay. But I know that I'm supposed to start with a vowel. So I take one of these X's and put it in the first position. Oh, I hope that I can remember what I did before coming to the class. Okay. So I put it here. So one of these X's are gone. Okay. I put it here. And then let me see what I did. Okay, now I start arranging these objects next to this X. Forget about this one X that I put here. I calculate the number of items that I can put here. What is that? Can you tell me? I want to arrange these 5 X's with those, and I want to arrange them. So it becomes how many letters? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and 13. So I write 13 factorial. Yes? And I divide it by 5 factorial because of that. 2 factorials because of n. 3 factorials because of t's. Yes? Am I right or not? For the time being, what I have done, I haven't solved the original problem. I have solved this problem that I put an x here, and what is left for me, I arrange them. Yes? Now assume that, imagine the arrangement is done. You see how many x's? How many x's you see in the string? 6, because I have only 6. One of them is the first one. Now, imagine that you want to distribute these letters onto the positions of x's. So do you understand what I mean? Let me write it for you. So here, for example, one scenario is this. One scenario is I start with an x, but I, for example, and then I ignore this, I write this one. For example, I have one c, I have another, for example, 2 x's, I don't know. I have one s, one n, one s, one this one, and I have x, 1, 2, 3, 4, 5, and then I have L, then I have T, then I have X, then I have T and T. Is it complete yet? 1, 2, 3, I'm counting in Persian. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. That's correct. So do you agree what I did? This is one of those items that I calculated here.
Yeah.
Okay?
Yeah.
Now what I want to do, x's should be replaced by these letters.
Yeah.
If I do that, then I am done. Now tell me, how many positions I have? 1, 2, 3, 4, 5, 6. Yes? How many ways I can put these letters into the positions specified by x's?
4.
No. How many? 1, 2,
Oh, 6.
3, 4, 6 factorial.
Factorial.
But 2 of them are of this type.
So,
2 of them are of that type.
and then you don't.
And that's it. 1, 1. Yes or no? Okay, and then can you tell me what I'm going to do now? What I'm going to do now?
Is that you can take total number?
No. You see what I did? This is not easy. You need to be a little bit experienced. I have seen these tricks before. Okay? So what I am doing, I am saying that instead of solving this problem, which we could solve and got this number, that's okay. But now let me tell you another way. I want you to understand that. I am telling you, forget about this problem. Consider this new problem. Okay? You have 6 x's, and I ask you how many of them start with an x. This is extremely simple problem, yes? Because when I say how many of them start with an x, you take one of these x's and put it here, then you will face 13 objects with some repetitions, which is a standard problem. So that is your number, okay? Now, this is this problem. My original problem, I do not have x's. Some of them are supposed to be occupied with O's, some of them should be occupied with I's, and one of them with U, and one of them with A, yes? In how many ways I can replace these letters in the positions that are designated by x's? That number.
Yes.
6 factorial. Oh, then what do I want to do with these two numbers to get the same answer? The question, should I add these numbers or multiply them? Should I add the numbers and multiply them or multiply them? You see, this is sometimes really confusing. Don't cheat to see which one will work, okay? Use the ideas, should I multiply or... So let me tell you this guidance once for all. If I stop here, is the task finished?
No.
It is not finished, yes? Because what I have done, I have just made this combination. Is this the one that I want? No, because excess, after that, excess has to be replaced by this. So if I stop here, the task is not accomplished yet. I have to continue to another stage, the task will be accomplished. So this means it's product. Yes or no? So this means that I have to multiply. But I hope that I haven't messed up. Is this number that number? By the way, here you use addition and product rule. Here I am just using the product rule in a little bit strange way. But let us see, is this number, can you confirm these numbers are the same? If you can, I don't know, hopefully I haven't done mistakes. Are these numbers the same? Because I don't see any mistake in my strategy. If they turn out not to be the same, it means that totally my idea was wrong. And I have been in that position hundreds of times, you know. This is very natural when it comes to combinatorics. You think that this is not possible, that I have done any mistakes, but they can show you, no, you can do it. Especially if you can do some coding, immediately you realize what is your mistake. Okay, confirm this is this one. How many of you confirm that? Okay, Elias, do you confirm these are the same or not? Okay, can you elaborate more?
We can simplify the 6 factorial and 5 factorial.
Exactly. So this 6 factorial, it can be written as 6 times 5 factorial. So far so good, because I get rid of this 5 factorial that I don't need. But what is left is 6. What is 3 factorial? 6. So that is also gone. So I am left with 13 factorial, 2 factorial times 2 factorial times 2 factorial. So the answer is 8. So you see, this is a little bit a strange strategy to tackle the same problem. But it is actually more advanced. Yes, because you can calculate, you see it is completely irrelevant if the number of items are repeated or not. You can always consider this scenario, and then instead of the excess, you can count another time and then multiply. Yes? Okay, now let me switch to a totally different problem. Okay, this will also help, and that is also very famous in combinatorics. And that is the ant problem, yes? Not uncle and aunt, you know, the insect ant, yes? So you have a checkerboard, but this time these are rows for this poor ant, yes? So here you have 1, for example, 2, 3, and 4, okay? And then let us consider that we have 1, 2, 3, 4, 5, 6. Okay, I want to be very regular. Okay, good. This ant is here. It is supposed to go to here. But in each step, this ant can go 1 unit to the right or 1 unit up. That's it. Okay? In how many ways this ant can reach there? Yes? So this is a good problem because it broadens the way that you look at things, you know. Because we learn things abstractly, but this is a little bit more intuitive. So you know that, for example, this is one possibility. This is one path, yes? So this is going to the right, 2 units up, right, up, 3 units right, up, and 2 units right. This ant will reach there. But of course, this ant can choose completely different. So this ant can go here, 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 and then the rest of it like this. Something like that. So in how many ways this can be done? 2 rows are considered different if they at least differ at least by 1 second. So in how many ways we can do that?
And you cannot go back, right?
No. According to this, going back makes the problem very hard. So because you can go back and forth, how many hundreds of times, and then it starts going to the right, you know. You're accelerating, going back and forth. So you cannot solve that problem. Yes, Ruben?
I think 13 factorial over 8 factorial times 5.
But I don't know, but I think your strategy. Tell me about your strategy.
Because you can look at it as ordering either going to the right or going up in different
Exactly.
ways.
So instead of counting this geometrical object, we can count the number of codes. The codes, let us denote this by up, and let us denote this movement by R to the right. Okay? This end goes from here to here at the end. So this end should go 1, 2, 3, 4, 5, 6, 7, 8 to the right, no matter how it will move. And 1, 2, 3, 4, 5 up. So for example, can you give me the code corresponding to this black road? This is R, U, R, yes, U, R, U, R, 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 U, R, R. So if I give you this code, you can immediately decipher the route, yes? Is that clear? Okay, so the point is that, can I give you another code for this orange one? Yes. It becomes what? U, 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 R, U, and then the rest of it is R. Yes? But it doesn't matter. I want you to understand, I am not counting the geometrical object here. Instead, I can count the number of arrangements here. I hope that you agree that they are the same. Yes, the numbers are the same. They are totally different things. That's just a letter consisting of R and U. This is a geometrical object. But the numbers are, the number of items here and the number of items here are the same. So instead of counting this one, I count this one. But this is very easy. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 objects are there. But not all of them are repeated, are this thing. 1, 2, 3, 4, 5, 6, 7, 8 of them are R, and 1, 2, 3, 4, 5 of them are. That's the total number. Yes? Is that clear? But let me ask you one more question. Assume that this ant is supposed to meet his cousin here. Okay? And then go to the journey to the grandma together. In how many ways they can do that? Yes? How many ways? This ant can visit the cousin, take him or her, and go here. In how many ways if that wants to do this? Or at least give me the strategy. So let me designate it here exactly. So this is the stop point. So for example, this road shouldn't be considered into account anymore. This road should not be considered anymore because they are not passing through this point. How many of them are passing through that point? Yes?
Wait.
A strategy. You don't need to be worried about the numbers. So what is your strategy?
I divide it into 2 trips, so I don't count it as one.
Yes?
And then I add them.
Okay, so let me just, yes, that's correct. So let me tell you, 1, 2, 3, 4, 4 units to the right. So you have 4 letters of R involved, but 2 letters of U involved.
Yeah.
Yes? How many ways I can arrange them?
So 6 factorial.
Yes.
And then divided by 4 factorial multiplied by 2 factorial.
Okay. And then now you are here. So 1, 2, 3, 4. 4 R's again. Yes. And how many U's you need? 3 U's. Yes. So what is the answer?
7 factorial divided by 4 factorial.
Okay. What should I do now?
You add them.
You add. How many of you agree? Still you are confused. You multiply.
Why?
What?
I do remember when I told you, you said that this is not possible, that I confuse multiplication and addition. You have to multiply. I told you, because your goal is to visit your sick grandma. Okay? you stop here and forget about your grandma. Okay? Or you start from here and go to your grandma. Your task is to reach to this point.
Yeah, of course.
If you do this, the task is not accomplished yet. The task is accomplished if you go take your cousin and move together to grandma. So whenever you have and, that's a rule of thumb. It should be multiplied. And if you have or, it should be and. Yes? Don't make that mistake anymore again. Let me ask you one question. Now suddenly this and realizes that he doesn't like this cousin. So he wants to avoid the cousin. In how many ways this can go to grandma without even getting close to the cousin? Yes? So what's the answer now? That is your problem for the next time, okay? Think about that. We want to go from here to here, but we want to avoid this particular point. And how many ways we can do that? Thank you very much. Now, Combinatorics is really, really fun. Yes. Thank you very much. Bye-bye.